All right, so in lab we already did a little bit of acid-base chemistry. But before we delve into the chemistry behind this, let's just define acids and bases using some simple terminology. How can you tell if a food's acidic? Does anybody know? So you could measure the pH level if you've got chemistry equipment at home, but just by taste. What do acidic foods taste like? Sour. So like a lemon and orange, things like that, have citric acid in there, making them acidic. They tend to have kind of that sour taste. It's a little bit different than a base. A base is something that's more bitter, which I know can be easily confused as sour. But if you've ever had something like tonic water, has anybody had tonic water? It tastes really bitter. Some people really don't like it, but tonic water has a base in there that makes it very bitter and astringent. All right, acids, on the other hand, can be detected using litmus paper. So let's say we have blue litmus paper. What will the acid do to that? It'll turn it red, right? So it turns blue litmus red. What will a base do with blue litmus paper? Nothing, right? So a base won't touch blue litmus paper. However, if you've got red litmus paper, it will turn it blue. That was something you saw in your acid-base lab. All right, what about acids reacting with metals? What do they do when they come into contact with the metal? They corrode them. So do you guys remember taking magnesium metal and we put it in acid? What happened? So you're thinking of the battery lab. Think back with the water lab when we had the magnesium strip. It dissolved. What happened when it was dissolving? It released hydrogen. So you guys captured the bubbles coming off the metal. Do you remember that? So acids are unique that way. They'll react with active metals. To make H2 gas. And we tested that with the match, and that gas made a loud pop noise, right? You can also react an acid with a base. And this will make water. And a salt. So for example, when you guys took potassium carbonate, or sorry, not potassium carbonate, sodium carbonate and sodium bicarbonate in the carbonates lab, you put in HCl, right? That created a water solution, and then you had that salt left over, and that's what you were measuring. So that's a common thing with acids too. Bases, on the other hand, also will react with acids. So they're similar in that way. And then the last one for bases too is if you ever spill a base on your skin, it tends to feel pretty slimy. Does anybody know why it feels slimy? Kind of, yeah. It's actually reacting with your skin, and you can actually feel your proteins denaturing a little bit, so it feels slimy. That's why you don't want to get strong acids or bases on you, as it will react with your skin and cause damage. All right, so let's look at some household items. I want you guys to help me decide which one's the acidic sample and which one's the base sample. Base on the right, acid on the left. Why acid on the left? Yeah, we've got some lemons in there. We've got vinegar in there. That's also pretty sour. Where bases are things like baking soda, ammonia, drain cleaner, even the antacids that you take. So in the acid-base lab, it asks you about antacids. Those are all good bases. They're used to neutralize the acid in your stomach. So over here, we've got acids that are common, and over here, we've got bases. Pretty easy to identify the common ones. There are some, however, that aren't very easy to identify. Yep.
So aspirin is acidic?
Yes, it is.
In the lab, it turned blue.
It did?
Yeah.
Interesting. That's an unusual result. So aspirin is acetyl salicylic acid. So in the name, it even calls it an acid, but we most commonly refer to it as aspirin. Yeah. All right, and then we saw the acid-base indicators, and we said that bases turn red litmus paper blue. That was a really common one. I know it's a little hard to see on here. And then acids turn blue litmus paper red. It's really easy to identify an acid or a base using just plain old litmus paper. The other one I like that was pulled from the book were these flowers. Does anybody recognize these? They're hydrangeas. And I had no idea about this, but if you look at hydrangeas, they're either blue or pink. Sometimes you would get white ones. But that actually has to do with the soil that they're in. So for example, blue hydrangeas are grown in acidic soils. And the pink ones are in basic soils. They're similar to cabbage that way, where they've got pigments in them that will change color depending on the soil type that they're in. So there are quite a few plants that have these really unusual pigments that change color based on pH. All right, and then the last one we saw in lab were these cabbage indicators. All right, so going back to lab, who remembers which side's more acidic? Is it going to be the green side or the pink side? Pink side. So pink side we said is going to be acidic. You can do this at home, grind up some purple cabbage, test it on whatever you want, and if it's turning more pink, then you know it's going to be acidic. If it's going more green, you know it's going to be more basic. Which one do you think is neutral? Purple. Just the plain old cabbage color. So you can use this to kind of get a rough indicator at home, which is kind of fun. Are there any questions with the basics? No pun intended. No? All right, nobody laughed. So let's define them using more chemistry-related terminology instead of just slimy. There's a few different definitions that are used. The first one that was developed was called the Arrhenius definition. And the Arrhenius definition was developed in, I believe, the late 1800s. And it was a simple idea that acids produce H plus in solution. H plus, if you remember, is a proton. So let's take a look at an example of this. Let's say I have HCl. We know it's acidic because it will dissociate into H plus and what else? Cl minus, right? So chloride. If we have HNO3, what do you think it's going to dissociate into? H plus. NO3, in order for this to be balanced, has to be negative, exactly. So hydrochloric acid and nitric acid are strong acids, and the thought was, well, when they go into solution, they're forming anions and cations. The cation in this case is going to be a proton, so they're acidic. And then they would try to define bases using similar methodology. So bases produce OH minus. What's this called? Whoop. Cheating. Hydroxide. In solution. So let's take a look at some common bases. Let's say I've got sodium hydroxide, and I'm going to dissociate this. What anions and cations will I get out? Yeah, Na plus. Sodium's always going to have +1. And then hydroxide, we know, must be -1 to balance that out, right? So the thought was that sodium hydroxide is a base because you're producing this hydroxide anion in solution. Does that make sense? It's pretty good definition, but it's not the best definition, and we'll talk more about that in a second. So let's take a look at one of the charts from the textbook. We've got some tables for common acids and common bases. So let's go through the acid ones. We've got sulfuric acid. If you've ever opened up a car battery or picked up a car battery, you'll feel that it's full of liquid, right? That liquid in there is actually sulfuric acid. That's why you always want to dispose of batteries at the recycle centers. You don't want to bust that open. It'll cause serious problems. The next one is hydrochloric acid. That's also a strong acid. That's used for cleaning metals, and it's also found in your gut. That's gastric acid. The next one is phosphoric acid. That's actually found in things like Coke, which is why they say Coke is really bad for your teeth. If you drink too much Coke, it will actually erode the enamel, because the enamel is likely made up of what? A base, right? Or a bone that has base in it. All right, the next one is lactic acid. If you're an athlete or if you just are super out of shape, you've probably felt this acid, right? That's the acid that builds up in your muscles when you're tired. So if you've ever gone running and felt that burning sensation, that's your body producing lactic acid. It doesn't feel very good. It's also found in yogurt. The next one is acetic acid, which is basically just vinegar. So you probably had that on your salad on occasion. Boric acid's the next one down. That's a weak acid. That's used in cleaning detergents and some cleaning products. So typically you'll find a little bit of boric acid in that powdered detergent that you add to laundry. The next one is hydrocyanic acid. This is super duper nasty stuff. It'll kill you if you ingest it. If you've ever watched the old spy shows where they have the pill and then they bite down on it and commit suicide, that was a cyanide derivative. It's very bad for you. Moving on to bases, we've got sodium hydroxide. Sodium hydroxide is used for making soap. Same thing with potassium hydroxide. They make different types of soap. That's going to be one of our last labs, is making soap. Lithium hydroxides used in making batteries. So lithium batteries oftentimes have an electrolyte made of lithium hydroxide. Calcium hydroxide and magnesium hydroxide are a little odd. They're not very soluble, but they're found in rocks, so they don't dissolve into the water very easily. But if you do spray an acid on them, those rocks will dissolve a little bit, and we'll talk more about that later. Ammonia is the last one. Ammonia is used in fertilizer and household cleaners, so Windex, if you smell that, that's the smell of ammonia coming off. All right, so one thing I did want to point out was if we look at the base one, what do you notice with ammonia that's not like the others? There's no oxygen in it, right? Up here we said bases should produce hydroxide, but down here I'm saying ammonia is a base, but ammonia does not have hydroxide in it, right? So the question is, what's going on? Is our definition good enough? Probably not. So that's why a new definition was developed. And this is called the Bronsted-Lowry Definition. And the Bronsted-Lowry definition is a little bit more accurate than the Arrhenius definition. And it basically addressed the problem that not all bases produce hydroxide. And we said an example of this was ammonia is a good base, but it's not something that contains hydroxide, therefore it can't produce it. There's also another problem. The other problem is, if we look at the Arrhenius definition, we said acids produce protons, but subatomic particles just don't float around in space like that, right? It's kind of weird to think about it that way, but they don't exist as free-floating protons in solution. That just doesn't happen. So protons, H+, don't exist in solution. So the Arrhenius definition is a little bit flawed. So they had to come up with a new definition. And the new definition is a lot better, but it also makes more sense. The new definition is that acids donate protons and bases receive protons. So the way I like to describe this is more of a handoff of a proton. The proton's not existing by itself in solution, it's getting handed off. Yep? That's ammonium. So the ammonium cation is NH4 plus, but NH3 is actually neutral. It's a little bit weird. They sound similar. Okay, so we said acids donate protons, bases receive protons. I like to think of it as kind of a handoff of a baton, right? So if you've ever seen a track relay, how many of you guys have seen a track relay? So in a track relay, right, the first person goes, takes the baton and hands it off to the other person. The atom that's handing off the proton is the acid. The other molecule that's receiving it is going to be the base. However, in a relay, you don't just throw it, right? You have to hand it off. So that's a more accurate description of a proton transfer. Is the proton doesn't exist by itself at any point in time. It's just being handed off. So let's make a little note of that. Does baton have two T's? One T? I've been in school for a long time, but my spelling still sucks. I'm sure you guys have spotted some of my errors. All right, so the proton is handed off between our acid and our base. So let's take a look at some common acids and bases, and I'll show you guys how organic chemists like to show this. So this is ammonia. Is ammonia an acid or a base again? It's a base. And let's pick an acid. Does anybody have an acid they want me to use? HCl. HCl is easy to draw, so I'll go with that one. So this is our acid. So if we are looking at this, right, this proton is going to be transferred to the base, right? So imagine the acid's the relay runner in front. The base is going to go and try to receive that proton. So the way organic chemists show this is they show this lone pair on the base basically reaching out, grab that proton, and then these electrons that are right here have to go somewhere after that proton's grabbed. So these electrons will actually hop over onto the chlorine. So let's finish this equation. All right, if we think about chlorine now, does chlorine have a charge? Is it positive? Is it negative? Is it neutral? It's negative. It's got one extra electron. So we'll put a negative charge in the top corner here. What about the nitrogen? In order to have a balanced reaction, we have to balance out cations with anions, right? So that nitrogen must be positive. So in this case, we've handed off that proton from the acid, the HCl, to the base. So the base is essentially stealing the proton from the acid. So this is a classic acid-base reaction. You guys want to try a couple other ones? Okay, let's do a couple others and we'll try to do it similar. Let's do Na plus HO minus, so that's our sodium hydroxide. And then over here, I'll have water. And then I'll do another one below too. Let's do HCl again. I'm going to draw it a little bit differently. And water. So first thing I do is I try to identify my acid or my base. So if we look at sodium hydroxide, Is that going to be an acid or a base? It's got to be a base, right? Which means water in that equation must be what? An acid. Okay? Okay, so we know the base is going to steal a proton from the acid. And let me draw in the rest of my lone pairs here. I'm getting sloppy. There we go. All right, so the base is going to reach out, grab a proton from water, and am I done? No, we've got to move the covalent bond electrons over to that oxygen. Okay, so on the left, we now have Na plus. And then what else? What does this guy form after it steals a proton? So hydroxide after it steals a proton? It'll just become water, right? So OH minus after it gets an H plus just becomes H2O. And then over here, what's going on with our acid after the proton's gone? It becomes a base again. So it would become hydroxide, OH minus. So acid-base reactions just involve this handing off of protons from one molecule to another. Let's do the next one though. So HCl. Yep.
Well, I just go like back and forth then. There's a water base, maybe a water base.
Exactly. So we're going to talk about that more, but that's referred to as an equilibrium if really you're going back and forth a bunch. So HCl, that bottom one, is that an acid or a base? Acid. Which means our water in this case must be what? A base. That's the weird thing with water. Is the pH of water, neutral water, is 7, right? Which means it can be kind of on either end. It can act as an acid or as a base. It depends on what it's around. So in this case, let's try to do the same arrow pushing. Okay, so oxygen's the base, so it's going to be the thing grabbing the proton, which means one of these lone pairs is going to reach out and grab this proton. The covalent electrons here are going to hop over onto the chlorine. And let's draw the other side of the reaction. Over here we've got chlorine that now has 8 electrons around it, which means it has what charge? Negative. Okay, and then what else will we have? HO3? H3O, right? Okay, so now we've got oxygen with 3 hydrogens and only 1 lone pair. So what charge must that oxygen have now in order to keep things balanced? Positive 1, right? So there we go. The Arrhenius definition we said is somewhat flawed because protons don't exist as free-floating particles, right? They're handed off like batons. And we said that not all bases produce hydroxide. Bases are just the things that are receiving the protons. So this is a much better definition that's used a lot as you go on into chemistry. Does that make sense? I know the arrow pushing can be tricky. I'm not going to stress that too much. I want you guys to understand the concept, though, of it being a baton getting handed off, though. All right, so now let's talk about what makes an acid strong or weak, because if we go back up to the table, we saw some of them were listed as really strong acids, other ones were listed very weak. How can we predict that, and how do we represent that? So let's go to our next section. Strong or weak. So the easiest way to define this is that strong acids completely dissociate. And so what do I mean by that? I'll do an example. So HCl plus H2O was the last example we saw. After they reacted, we said we've got this H3O plus. Let me include my lone pairs here. Plus Cl minus, right? If we were to go and measure this, we would say, all right, we've got 100% ions in solution. After we mix everything up. So there's no more HCl left in solution. In fact, it's only H3O plus and Cl minus in solution. That's what a strong acid is it's 100% ions in solution. And so we represent that by using a one-way arrow. So right here, you notice how the arrow is only going one direction. It's not going backwards at all. It's only going in the forward direction. Okay? That means that weak bases are bases that don't completely dissociate, right? Or sorry, weak acids. So let's take a look at an example of a weak acid. If we go back to that table, the weak acid that was shown was HCN, cyanide. If we treat this with water, because it's a weak acid, it doesn't want to let go of its proton very much. It wants to hang on to its own proton. So we might observe a little bit of H3O plus in solution, plus a little bit of Cn minus. Let me move this over. However, only a tiny little bit's going to be going in the forward direction. Most of it is actually going to stay on the left-hand side. And so the way we represent this is by using this special set of arrows. So instead of having an arrow only pointed towards the right-hand side, you show a little bit of I guess I should say a half arrow where it only has one barb coming off on the top and then one barb coming off on the bottom, and then the bigger arrow is pointing to the side of the equation that's more favorable, right? So if we look at this, let me change this. There's very little ions in solution after being mixed. And you can tell this arrow right here prefers to stay as starting materials. Does that make sense? It's a little bit weird. Oftentimes, too, you may see equilibrium arrows that are even. So, for example, you may see equilibrium arrows that look like that. What do you think that might mean? It means it could be 50% on starting material side, 50% on products side, and everything's switching, going back and forth at all times, right? So 50% starting materials in solution, 50% products, and it stays there. So that's defined as an equilibrium. It means it's pretty happy being mixed between starting materials and products. Does that make sense? All right, so let's define one last thing. Acid strength is an intrinsic property. Meaning it does not have to do with concentration. So that's something that throws a lot of chemistry students off, is they say, well, because something's concentrated, it must be strong, right? You can't really use that terminology interchangeably. Strong acids are by their very nature strong because of the molecules that are inside of them, right? That being said, concentrated strong acids are a lot more dangerous than dilute strong acids, right? So for example, if we had sulfuric acid that was diluted to 0.000001 molar, sulfuric acid's still a strong acid, but it's very dilute. It's not likely to hurt you when it's dilute. However, if you had concentrated sulfuric acid, let's say 18 molar concentrated sulfuric acid, that will really mess up your skin and give you a permanent chemical burn. So they are separate concepts, and you have to be careful when you're talking about strong versus weak acids. It's not related to concentration at all. Does that make sense?
Is it like watered down Coke?
Yeah, like watered down Coke. It's still Coke. You haven't changed the Coke that's been watered down, but now it's not as strong as it used to be. Okay, let's move on to neutralization reactions. Okay, neutralization reactions are when you react an acid with a corresponding base. And when you do this, it's called a neutralization reaction because the final product's neither acidic nor basic. So let's take an example of this. And the example I like using is just plain old HCl with sodium hydroxide. I'll do NaOH plus HCl. HCl is our acid, sodium hydroxide is our base. The question is, what's going to come out of this reaction? So what I like to do is at the first step, break everything into ions, right? Sodium hydroxide is a strong base, HCl is a strong acid. That means they're going to dissociate completely. And then I combine everything back together. So sodium hydroxide would be Na plus, OH minus. Oh shoot, sorry, my pen's getting flaky. And what would happen with HCl if we show it breaking apart into ions? What do you guys think? It'd be H plus and Cl minus, right? Okay, so now we've got all these ions floating around in solution. Now what we need to do is combine them together in order to make water and salt. So let me put that in parentheses there. So in order to make water, all we're going to do is combine the OH minus and H plus, right? What do you think the salt's going to be? What's the name of the salt? The Na plus and Cl minus, sodium chloride, right? If we look at the products of this reaction, we've got water, which we know is neutral. And sodium chloride, that's not an acid or a base. So this is an overall neutralization reaction. Oftentimes too, if we're just showing this as a compound, we omit the charges and we would just show these as our final products from this reaction. So it's a neutralization reaction because you're getting rid of your acid and your base, and you're forming salt plus water. You guys want to try a couple more practice ones? Okay, I'll give you guys a practice one. Calcium hydroxide plus hydrochloric acid. So you're going to have to convert calcium hydroxide to its molecular formula. Same thing with hydrochloric acid, but we just worked with that one. So what's the formula for calcium hydroxide? Is it just CaOH? What's the charge for calcium? +2. What's the charge for hydroxide? -1. So we need 2 hydroxides to balance out the +2 on calcium. So I'm going to do parentheses OH2. And then I've got HCl. And our goal is to figure out what's coming out. We know it's going to be water. That's one of our products. What's our salt going to be? Calcium chloride. Okay, what's the molecular formula for calcium chloride? Is it going to be CaCl? CaCl2, right? Because calcium's +2, we need 2 chlorines. Okay, is this equation balanced? What are we missing? So we're missing a 2 in front of the HCl, right? We've got 2 chlorines here, so we must have 2 chlorines over here. Now is it balanced? Two H2Os. Okay, so now let's double check. On this side, we've got 2 hydrogens, that's 4. And over here we have 4. So the hydrogens are balanced. Let me erase this. Let's do calcium. We've got 1 calcium on the left, 1 on the right, so that's balanced. Now let's do oxygens. We've got 2 on the left, got 2 on the right, so that's balanced. If we look at chlorines, we've got 2 on the left, 2 on the right, so it looks balanced. Let's do this using pictures, and hopefully we can make more sense of this too. I'll do this in green. So I've got Ca2 plus floating around. I've got 2 hydroxides floating around. And then over here I've got HCl's. I've got 2 of them. And HCl, if we show it completely dissociated into ions, looks like this. And we're trying to form water in order to do the neutralization. So really all we're going to do is say, all right, these can combine to form 1 water molecule. These can combine to form our second water molecule. That gives us that gives us 2 waters. Right, those were the ones we circled, and that leaves us left over with 1 calcium and 2 chlorines. That's our calcium chloride. So CaCl2. So if you do ever have trouble with these, it can oftentimes help to break them all down to their ions, recombine them the best you can to form water, and then see what's left over. Whatever's left over is going to be your salt byproduct. All right, I think that's where we're going to stop today. Monday when we come back, we'll talk a little bit more about environmental chemistry too, which will be pretty interesting.